So in this video we want to show that a prime number p divides the binomial coefficient p choose k for each natural number k that is between 0 and p. To show that, we first use the definition of the binomial coefficient, which is p factorial divided by k factorial times p minus k factorial. We can unwind the factorial to p times p minus 1 times so on times p minus k plus 1 times p minus k times so on down to 1 divided by k factorial times, and now we unwind this factorial, p minus k times the other factors down to 1. And we see we can reduce the fraction here, and we get p times p minus 1 times some factors times p minus k plus 1 divided by k factorial, and we unwind this to k times k minus 1 times so on times 1. And this fraction we call now a divided by b, which is equal to a number t. And we can easily see that a is divisible by p, because p is one of its products, of one of its factors. And b is not divisible by p, because p is a prime number that it's larger than any of those factors, and therefore it does not divide b. And we can also see that t times b is equal to a. And we know that a is divisible by p, and therefore the whole product has to be divisible by p. But b is not divisible by p, therefore t has to be divisible by p. T is divisible by p, but only if t is an integer. But how do we know that t is an integer? Because it's defined as a fraction. We can show that with the rule for the binomial coefficient, which states that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. And this rule holds for k between 0 and n greater or equal 0, and k and n are natural numbers. Okay, how do we prove it? This part is equal to n minus 1 factorial divided by n minus 1 minus k factorial times k factorial plus n minus 1 factorial divided by n minus 1 minus k minus 1 factorial times k minus 1 factorial. That's just plugging in the definition. Now we can factor out the n minus 1 factorial and get 1 divided by n minus 1 minus k factorial times k factorial plus 1 divided by n minus k factorial, because those two ones cancel each other out, times k minus 1 factorial. And that's equal to n minus 1 factorial. This part stays the same. And now we extend the fraction. The first fraction gets extended by n minus k. And therefore we have n minus k factorial times k factorial. And the other fraction gets extended by k. So we have k divided by n minus k factorial times k factorial. And we see the denominator of those two fractions is the same now, so we can add them easily together. N minus 1 factorial times n minus k plus k equals to n divided by n minus k factorial times k factorial. Now we multiply n minus 1 factorials times n, which is n factorial, divided by n minus k factorials times k factorial, which is by definition the binomial coefficient of n choose k. So we have proven that this rule holds, and for the special cases that we have n choose n, so n and k is the same, we have n factorial divided by n factorial times n minus n factorial. So those two cancel each other out, and this is the factorial of 0, so 1. So we get a 1. And the same for n choose 0. There it is, n factorial divided by 0 factorial times n minus 0 factorial. So this is n factorial, this is n factorial, they cancel each other out, and that's just a 1. So we get a 1 here too. And this rule is basically the rule for the Pascal's triangle. So 0 choose 0 is equal to 1. 1 choose 0 is equal to 1. 1 choose 1 is equal to 1 is equal to 1. 2 choose 0 is equal to 1. 2 choose 1. There we can use the rule. We add those together, so it's 2. And 2 choose 2 is 1. And we know the beginning here, those binomial coefficients are all integers, and new binomial coefficients are produced by adding integers, so we get an integer here as well. Therefore we know that this binomial coefficient is an integer, so we see that p divides this binomial coefficient, which is what we wanted to show.